we have a function or an operation that we're defining with a star. So x star y, and x and y are two elements from the set that we're operating on. And the result is we're going to take x and y and add them together in the usual sense, but we add one on after every operation. So every time we star something, we sum them together and then we add one to that. Okay, and so we're going to check is this an associative property? Is it commutative? Does it have an identity? And we'll look for an inverse. Okay. So we're going to go through this checklist of things just to make sure and see if this satisfies any, all, or none. Okay. So in the first case, let's check out the associativity. So we're going to need three elements. So let's call it x, y, and I guess we'll use z. And these are elements in the set that we're pulling this from. Okay, so for these three elements, hopefully it's not so blurry that you can actually see it. Okay, so we're going to look at the associativity. So we have x star y star z. And if it's associative, we should find that that is equal to x star y star z, where uh, the we first do the second two elements and we operate on them, and then we operate on that pair with the third one. Whereas in this situation, we're operating on the first two and we operate the first two, then with the third one. So the order in which we are operating on the objects changes with the associativity. And so let's see if this equality holds. And so we're literally just going to test it on one side and then on the other side and see if the comparison of the two sides are the same. Okay, so starting on the left-hand side, we have x starred with y starred z. Okay, what does that look like? Well, this is x starred with y plus z plus 1. Okay, so that's using the definition of the operation here. So now we have them written as a sum. And now I'm going to operate on this thing. So think of this as one unit, and I'm starring it with this, which means I'm going to have this thing added to this. So this is going to equal x plus y plus z plus 1. Kind of think of it as like putting it in parentheses-ish, and then on that you're going to add another one. Okay, and so the parentheses here are just to kind of help see the focus here. I was trying to write them like lighter, but they're gone. And so now we have x plus y plus z, 1 plus 1. So we have x plus y plus z plus 2. Okay, so that's what happens when we operate on the first or the last two objects and then operate on the third or on the first one. Okay, so let's try that again now with x star y star z. So operating on this, we're going to get x plus y plus 1, and that then gets started with z. And so again, just like as before, we're going to operate on this as one unit with this. So it's going to be x plus y plus 1 plus z plus 1. And then given that these are all elements, let's say the real numbers, I can shuffle this to the 1 and make that a plus 1. And so this is going to be x plus y plus z using the commutative property of the real numbers, and then plus 2. And so since these two are the same, it turns out that this is associative. Okay. All right. Now let's look at, let's see, commutative is next. So associative, check. Commutative means that x star y should equal y star x. So let's check the two sides. So x star y is going to equal x plus y plus 1. And if we check y star x, what's that going to equal? It's going to equal y plus x plus 1. Okay. And given that these are, let's say, real numbers, then I can rewrite this one as x plus y plus 1, which is identically equal to those two are exactly the same. And so it checks that it is in fact commutative given this set. And then let's see, we want to check the identity. So identity, what that means is X starred with some uh, identity element. We typically call it E. For whatever reason, this isn't the function E, but it stands for the identity. We want to see if that gives us back X. Okay, so is there some quantity that would allow for us to do that? And so let's check this out. What is X star E? Well, that's going to be X plus E plus 1. And so if E is the identity where we get back X, that means that E would have to equal -1. And so if we let that be the case, then X star E would equal X plus a -1 plus 1, which would then equal X. And so it does have an identity. If we let the identity equal the -1. And last but not least, so check here. What do we want to check? We want to check the uh, if every element has an inverse. So does this have an inverse? So maybe if I make a little room here. So what does that mean? So inverse means that if I take X, and I start with X inverse, that I should get the identity, which is what we just found is -1. That's what we just found here. Okay, so let's go ahead and see what that might look like. So X star X inverse is equal to X plus X inverse plus 1. And we want to equal that to -1. Okay, and so what would that mean? It looks like if we subtract 1 and subtract X from both sides, then this would imply that X inverse is equal to a -2 minus X. And so that would be the inverse element for any object X in the, and let's check it out. So we'll try with another element Y. So Y star Y inverse, what is that going to equal? It's going to equal Y plus Y inverse plus 1. But that equals Y plus a -2 plus a -Y plus 1. So those equal 0, and this equals -1, which is the identity. Okay, so in this case, it actually has all three. Okay, all right, that was a fun little example. I hope that helps to illustrate how defining an operation, and we can check then the properties that the operation is in fact satisfying those algebraic rules. If we look at the discussion in class about the elements that also make up an operation, remember it said that an operation is a finite, is a rule that assigns an ordered pair from so two elements pulling from it that it's still in. So we could check closure. So we didn't check, but we could check closure, making sure that it is that this thing is closed, and then also, and that would depend on where we're pulling our elements from. We want to make sure that it's well defined. So that'd be another element to consider. Uh, we also want to check that it's uniquely defined. Those three things would be additional things. And so if we're looking at, for example, the real numbers, if our x and y are coming from R, which is what we were assuming through the majority of this, then the sum of two real numbers is unique. It is certainly well defined because you're taking a linear relationship, so it's a linear equation. It's a line, and it is definitely closed because the sum of two real numbers plus 1 is still a real number. So these are really easy to check when our elements are elements of the real numbers, and those same properties hold for each of those elements. So there we go. I hope that was helpful, and I'll look forward to seeing you in the next video.